Okay, this is a quick video about collisions, something called the coefficient of restitution and center of mass frame and why it rules. Maybe you've seen coefficient of restitution before. It's this funny formula here, and it has something to do with the relative velocities after the collision compared to the relative velocities before the collision for two things when they collide. I want to explain where that comes from, why it's meaningful, and how you can use it to explain what's happening in this video. So first, I just drop a softball and it hits the ground. And that's about what you'd expect to happen. And then I have my assistant drop it on something bouncier. And there's not much change. And then I drop the bouncy thing and the ball together and lift off. It goes really high. I want to do a stripped down version of that problem and use these three concepts in order to explain why the motion is what it is. Okay, so the first thing we got to understand is what happens when you drop a ball on the ground. Well, if you hold it from a certain height h, the ball falls. It develops speed, and when it hits the ground, it has a certain speed. Now, the ball will either go back to where it started, we say that energy is conserved in that case, or the ball doesn't return to where it started, and then we say energy is lost in a collision with the ground. One way to express that is we can express it in terms of the final heights. In other words, this ball didn't go as high, so it doesn't have as much energy. But another way to look at it is that the ball must have left the ground with less velocity. In other words, after it collided with the ground, it didn't have the same amount of velocity it had before it hit the ground. And in this case, it must have had the same amount of velocity because it wouldn't have been able to get back up to h if it didn't. So instead of talking about this in these terms, we talk about the kinetic energy before the collision and the kinetic energy after the collision. And that goes like the ratio of the squares of the velocities. So this is what I want to do. I want to do a little bit of algebra and analyze a purely elastic collision where energy is conserved and understand where this coefficient of restitution comes from. So let's park those up there. We'll get ready to do some algebra. You can go through this as slowly or as quickly as you like. The first thing we do is we set up conservation of momentum. So this is momentum. And then we also say conservation of energy. In other words, I demand that the initial energy equal the final energy. This is two equations and two unknowns. It's a bear to do the algebra. Most introductory books do it about halfway. I'm going to do it all the way for you. So in this case, all I do is I just put, for the energy equation, everything involving V1 on one side and everything involving V2 on the other side. I factor it. In other words, this is the difference of two squares, so I can factor it that way. And then under it, I write the momentum equation. So this is the momentum equation rewritten with everything involving V1 on one side and everything involving V2 on the other. Now, the funny thing you do in order to do this algebra is you divide this equation by this equation. When you do that, these will cancel and these will cancel, and you'll end up with this. This is what you're going to end up with. And then most books stop here and they just say, after some more algebra, well, I'll show you what the algebra looks like. You solve for V2 final, you punch it back into the original momentum equation, which is this guy. You do a little bit of rearranging, and then you can solve. Once you solve for this guy, V1 final, V2 final is free. I didn't actually do the algebra to get this. I'll tell you a little secret. All I did was everywhere where there was a 1, I put a 2. And everywhere where there was a 2, I put a 1. This equation has to be symmetric. Of course it does. There's nothing special about 1 or 2. I didn't tell you anything about them. So once you figure out 1, you get the other one for free. Now, the thing I want to concentrate on this video is this line, which remember is part of my purely elastic collision. I want to focus on that for a second, and I just want to rewrite it slightly differently. I want to say that if I bring V2 over to this side and V1 over to this side, now look, here's the relative velocities again. If all I do is insert a coefficient E here, and I call E the coefficient of restitution, well then for a purely elastic collision, apparently E is 1 because I got this from assuming that energy was conserved. But I'm just saying maybe there's a way that I could slip an E in there when energy isn't conserved and my energy will just scale that way. So I don't say that that is correct. I just say we need to explore that. So I'm going to park that up there. I'm going to call this guy the coefficient of restitution. And this is what we're going to say. That E is going to be somewhere between 0 and 1. And if it's completely elastic, if energy is conserved, then E will be equal to 1. And if it's completely inelastic, then E will be equal to 0. Now, what does that mean? Well, let's take the case of my ball falling to the ground. Here it's a box. But you can imagine that if this guy leaves the ground with V initial equal V final, then it gets back to the original height it started at. And I say that energy is conserved. In that case, if I said that V1 final equal V1 initial, and of course the ground doesn't move in either case, right? Well, then that's good. That would give me E equal 1. Now, of course, the sign flips. I go from headed down to headed up, and you know that momentum is a vector, so you have to pay attention to signs. So this is actually good. The other thing is, if the ball just hit the ground and it just stayed right there and didn't do anything, right, then it would lose all of its final energy, would have none, and then the elasticity, the coefficient of restitution in this case, would have to be 0. So this squares, this makes sense. Here's what doesn't make sense. If I take two blocks and they're both moving and I smack them together and I demand that it's a sticking collision, in other words, V1 final equal V2 final, if that's the case, if V1 final equals V2 final, then my coefficient of restitution has to be 0. But clearly, I have some kinetic energy at the end. Perhaps not as much as I started with, but I still have some kinetic energy. So this elasticity can't quite be the amount of kinetic energy I have at the end. So what I want to do actually is examine this from the center of mass frame. If you recall, the center of mass is the average location of where all the stuff is. There's some stuff here, there's some stuff here. Now the center of mass is the average of where it all is, and even though these two things are moving toward each other, the average location of the mass doesn't change because neither of these guys' motion is changing. So that's the beauty of a collision. In a collision, the motion of the center of mass doesn't change. So if I choose to go in the center of mass frame, that means make the demand that the velocity of the center of mass is 0. How do I do that? I sit on top of the center of mass, and therefore I measure its velocity to be 0. So I'm making the demand that I do this calculation to find the center of mass, and it's 0. That's called the center of mass frame. Now remember that momentum is conserved during a collision because there are no external forces. There are no external forces, and so momentum is conserved. What does that mean? That means that the initial momentum is 0. This is the initial momentum rewritten as 0. This plus this equals 0, which is another way of saying they have to be opposites. And the final momentum is 0. Now I want to take a look at that coefficient of restitution formula again. And now what I want to do is use these relationships in the center of mass frame to see what this actually says. If I do that in the center of mass frame and I do a little bit of algebra and I plug some stuff in, what I will end up finding is that the coefficient of restitution is simply the ratio of the final velocity of one block to the initial velocity of that same block. Okay, why is this significant? I also want to examine this frame, the ratio of the kinetic energies. The ratio of the kinetic energies before and after the collision in this frame, making similar substitutions, is V1 final over V1 initial or V2 final over V2 initial. Apparently, I can look at, in this frame, I can look at either block by itself and determine whether or not kinetic energy is conserved. In other words, in this frame, in the center of mass frame, the coefficient of restitution is the ratio of the final kinetic energy to the initial kinetic energy. Now let's examine again that sticking collision. A sticking collision in the center of mass frame, since the center of mass can't move, once they stick together, nothing can move anymore because the center of mass is not allowed to move. That means that your final velocity is 0, and in this case, that makes perfect sense. Your elasticity, your coefficient of restitution has to be 0 in this case because there's no motion at the end. Okay, so my energy is lost in the center of mass frame, and all of it is lost in the center of mass frame. Okay, in other words, my final kinetic energy is 0. Okay, now let's attack a real problem together. Let's put all this stuff to use. So here it's basically the video I showed you. I just say one ball has a mass of 10 m. It's dropped from some height h, and another ball is dropped right after it. And I also say that assume the large ball has finished its collision with the ground and it collides with a second smaller ball. Treat both balls as point masses. In other words, I don't want to have to include terms that deal with radii and stuff here. It's not a big deal to add them, but it's not really what I'm interested in wasting calculation on. So let's just take them both to be point masses, and we'll have a situation where one ball is moving up and the other ball is moving down, and we'll examine two cases. The first case, coefficient of restitution is 1, so no energy is lost. Second case, coefficient of restitution is 0.5, and that means something about the energy in the CM frame. And so what we'll do is, we'll do both. We'll do them the hard way. And then I want to do the whole problem in the CM frame and show you how wonderful the CM frame is. Okay, so let's get started. Part A, perfectly elastic. Well, all of that terrible algebra that we did earlier produced this beautiful equation. In other words, I'm not going to go through all of it again. Rewind the video and watch the algebra again. All I need to do is plug and chug. So recall that if you drop something from a height h, by the time it hits the ground, it will have some velocity that's based on this. If I take that and I say that they both have the same velocity, and I plug in for the masses, Okay, and then finally, I plug in for this term the velocity. I'll end up with something that looks like 29 over 11 times square root 2gh. Okay, but the problem isn't asking about the final speed. The problem wants to know, how high does it go? Well, that's pretty easy. We just say potential energy equals kinetic energy. And so in this case, I end up with something that goes about 29 over 11 squared times h. So that's not particularly meaningful. I'll just tell you that's about 7h. That's pretty significant. In other words, if I drop it from my height, which is about, I don't know, say 2 meters, allegedly it's supposed to go 14 meters or 40 feet into the air. No way. I was there. I did it. It did not go 40 feet into the air. But apparently, if I was conserving energy, that is how high it would go. So that's so much for that. Let's move that guy up there. Now let's say the coefficient of restitution is 0.5. 0.5. Let's do the whole problem all over again. This time, I'm saying the coefficient of restitution for both collisions, in other words, the first ball M1, has to collide with the ground and come back up. And then I have to collide with the second ball. So there's two things to do here. Let's first deal with the impact with the ground. The big ball, right before it hits the ground, has 2GHs worth of velocity, and it's negative because it's going down. My coefficient of restitution is 0.5. And one thing to note here is that I'm colliding with the Earth, and the velocity of the Earth before and the velocity of the Earth after is 0. So that means that I should have my velocity after the impact with the ground. In other words, this big ball, when it goes upward, has half the velocity it had before it impacted the ground. So I take that, I park it up here, and I say that the little ball, M2, that has however much energy it had, because it hasn't had any collisions yet. Okay, now I have to do conservation of momentum. So here's my conservation of momentum equation. And here is my equation for the coefficient of restitution, which gives me a second equation because I have two unknowns again. I have V1 final and V2 final are both unknowns. So we can grind through the algebra. I simply plug in for the initial velocities, which I've already solved for. Okay, I do that in both, and I end up with two pieces of algebra that look like this. And then I can perhaps solve this one for V1 final and plug that into the other one. And I end up with something that's rather messy looking, but not terrible. And I can solve, and I get this thing 46 over 44 times root 2gh. If I grind through all the algebra, here's something interesting. By cutting the coefficient of restitution in half, I don't go half as high. I go basically to the same height I went to in the first place. And I definitely did better than that in the video. So my coefficient of restitution in the video is definitely bigger than 0.5. I couldn't say exactly what it was. Anyway, this is a lot of ugly algebra. And what I want to do is convince you to not do as much ugly algebra. Instead, I want to look at this problem in the center of mass frame. So first of all, what do we mean by center of mass frame? This is the Earth frame. These are the velocities that I just talked about. That's what it is for the person holding the camera, say. But if I switch frames and I go to the center of mass frame, well, first I need to calculate what the center of mass frame is. This is that same equation that I had before. It's M1 V1 plus M2 V2. Notice that minus sign there is because this guy is headed downward. It has a negative velocity. So apparently this is the velocity of the center of mass of the system. And so if I want to transform to that frame, well, then the velocity of 2 relative to the center of mass is the velocity of 2 relative to the Earth, plus the velocity of the Earth relative to the center of mass. If I punch in all of these numbers, I end up with this. So apparently, according to someone sitting on the center of mass, that second ball is moving at this speed. Now, here is the payoff. This is the beauty. In the center of mass frame, the coefficient of restitution simply means the ratio of the initial to the final velocity. So what does that mean? That means all I have to do is multiply my initial velocity by a half. In other words, it goes from 15 over 11 to 15 over 22, and instead of going down, it goes up. That's what that minus sign tells us. Okay, well, that's the final velocity in the center of mass frame. What about in the original Earth frame? Well, I just transform back again to the original Earth frame, and I do a little bit more algebra. I crunch some numbers, and I get 23 over 22, and in case you're not great at fractions, that's the same thing as 46 over 44, which is exactly the same result we got last time. So it's 1.09h. So look, the algebra is not terrible in this case, but the real idea is that the coefficient of restitution is a measurement of the initial and final kinetic energies, the ratio of those two, in the center of mass frame. The physical thing that's important here is the center of mass frame, and you can see that when you do calculations in the center of mass frame, it is easier. Okay, hopefully this video was more helpful than confusing.